There. Right, what I want to do is have a look today at heat and heat transfer. The vagaries of some of these systems. Okay, so we want to look at energy transfer by heating. There are three ways in which this can work. And we can look at heating simply by looking at the transfer of heat by conduction, by convection, and by radiation. So let's have a look at how this basically works and see what goes on. Now, heating by conduction is largely for solids. Convection is used largely for liquids and gases, and radiation tends to be used when we want to move heat, can be through a vacuum, but can be through various other media, can work through gases, not so well through liquids, but there's our basic idea. Well, that made it worse, didn't it? Right, okay. So let's have a look at what we can do. And we're going to have a look at a few experiments. I have done many of these experiments already on my YouTube channel, and we'll try and put a link to some of those at the bottom. But for the time being, let's go and have a look at a lot of these experiments and revisit them and see what we can do. So let's have a look at conduction first. I've got a series of experiments that I can do. I've got a whole series of boxes with bits and pieces here. And the first of these that I want to have a look at is this device. What it is consists of four strips of metal. Did we got the microphone following on? Yes, we did. Right. So we've got four strips of metal. Each of these has got one of these sort of forward thermometers placed on it. And this can be used to track the heat. So what I'm going to do is I'm going to take this beaker and I'm going to put a small amount of hot water in there. And we're going to put this into the hot water. I'm going to trace how the heat transfers along here to see whether copper, aluminium, brass or steel conducts the heat the fastest. Which one of these is going to be the best? Which one do you think? Now, Paul's just going to put the kettle on for me. And it might take a moment to heat up. Right. So how does this conductivity work? Well, the molecules are next to each other, and the molecules vibrate. And as this molecule vibrates, it starts banging the other one. And the other one starts to vibrate too. And that one then knocks onto the next and the next and the next. So what we can get is a whole series of molecules vibrating, banging into one another, and passing the heat along. And some of these are going to be better than others. Right, thank you. let's just put in a little bit of water. And we don't need an awful lot in here. Just enough to cover it. And what we're going to do is we're going to place these in the water. And I'm going to try and bring it close to you so you can see, hopefully, how it's going. And we can see the copper wins, the heat is transferred across there first. Aluminium is coming in second. Brass is still only about halfway. And the steel has managed just about a quarter. Now if I lay that down and I touch this piece of steel, it feels quite hot. This end, no difference in temperature. So this is hot, this is cold. This one's hot, this one's cold. This one's quite not as hot, and that's the same temperature. This one, again, about the same as the aluminium, and again, hot throughout, hotter, and colder, normal room temperature hasn't changed, and the hottest, and the same temperature as the brass, because the heat has yet to be transferred across. And we can see this still quite clearly. Put it around the right way so you can read it. So the steel conducts heat pretty badly. Brass quite well, aluminium very well, and copper is probably our best conductor of heat. So there we are. There's a nice simple experiment to show conduction. Now there are other ways of trying to show conduction, and one of those is by using a piece of paper, and I've got here a metal rod and a wooden rod. Now I've got a thermal thermometer. Yeah, it's hitting it. And hopefully, if I position this correctly, we can see that the temperature of this. Can you see that? It's about 27 centigrade, about 27. And if I take the wood, it's 26 centigrade. So the metal is 27, the wood is 26. The metal is actually warmer. But if I touch it, the wood feels reasonably warm, and the metal feels quite cold. Curious. So let's have a look and see what happens if I put this into a paper tube. I've got wood this end, and I've got metal at that end. Metal and wood. And what we're going to do is we're going to flip it. So metal at this end, wood at the far end. Let's see what happens if I pass this into the flame. And something's happening straight away. So what's happening here? Well, what we've got is where the wood is, the paper is starting to char. And where the metal is, it's not. If I take this out, you can see I've done this a few times before, and the wood has got slightly charred. This metal feels really quite warm throughout. The wood? No, hasn't really changed. Oh, that looks quite hot. Conduction. The metal has conducted the heat away. And as it conducted the heat away, it kept the temperature of the paper fairly low. The wood, on the other hand, did not conduct any heat away. It's an insulator. And so, because it didn't take the heat away, the heat stayed where it was, and the paper started to char. So, quite an interesting little experiment there to have a look at. Okay, so that gives us an initial idea about conduction. How about convection? Someone put a thing on my seat. Right, I think that was probably me. So let's have a look then at, first of all, what we've seen, and then we'll move on and have a look at the next experiment. And what I'm going to get Paul to do for me is I forgot to get a retort stand out and clamp. Could you get one for me? Sorry. Right, let's have a look. In the conduction, we've looked at two experiments. We looked at moving heat down a piece of metal, and the heat transferred from hot to cold, and we found that copper is better than aluminium, and aluminium is better than brass, and brass is better than steel. Can't spell. So if we want to use something to move heat around, then copper is our ideal candidate. If we can't manage with copper, and copper is running out, then we can use aluminium. And brass and steel are much less so, so they're not as useful to use. In the other experiment, with the piece of paper on the metal and the wood, we see that the metal conducts the heat away, so there is no burning, and the wood acts as an insulator, and there is some burning or charring because I didn't heat it that much. Right, let's have a look at our next item, and that is to look at the process of convection. Convection occurs in liquids and gases, and we're going to have a look at a couple of these to see what we can do. If you like to move the camera, refer that back for me. I want to have a look at, in particular, three different experiments to try and show this working. The first of these is really very simple. And what I'm going to do is I'm going to get out a large beaker of water. Paul, if I'd like you to give me about half a beaker of water. Okay. So what I'm going to do is I've got a beaker. I think we might go for a bit more. Double the amount of water. I think that might be better. We'll have a look. As usual, I don't have enough room around here to move. And what I'm going to do is Paul's giving me a lot of water. And what we're going to do is we're going to put that water on there. And what I want to try and do is I want to give this a moment to try and calm down. I've put the labels to the wrong side so they won't hopefully interfere with what we're having a look at. And what I'm looking for is to put in one crystal of a dye. We'll use this dye in a couple of experiments. So what I'm going to do is I'm going to put in one crystal of this, hopefully in the middle of this beaker. Okay. Now, what I'm going to do is I'm going to heat this gently in the middle. Just for a few moments, and let's see what happens. Unfortunately, it does mist up immediately. But I'm heating now directly under the crystal. And we can see, hopefully, there is a plume of the dye as it starts to dissolve. And what it's doing, it's rising up in the centre. When we see this in books, they draw a nice, pretty picture of this. And in fact, it looks nothing like that. And you can see it's going up, and then as it goes up, it's also then starting to fall down in various other places. So it's going up, and it's sort of moving around, and then it's starting to fall. And we've got a sort of a circulation starting. Well, this isn't really as good a way of trying to show this. So I've got a better experiment I want to do to try and show this. So I'm just going to put that down out of the way. And we're going to try and look at a slightly better version of this experiment. And with this experiment, what we're going to do, we're going to have a look at a tube. Now this glass tube we're going to fill with water. And then I'm going to put a crystal just here. If we heat the bottom of this, then if what's looking like that works, the water, when I heat it, will rise. Now, why it's going to rise is because as the water molecules become heated, they're going to start to move around more. There's going to be less molecules in the volume, so it's going to become less dense. So that water's going to rise. And as it rises, it's going to push the water around. So we're going to get a circulation. And let's see if we can see that working. So what we're going to do is we're going to set this up. I'm going to get some more water in a second. What I want to do is make sure that when I put this in place, it's going to be in the right place so I can actually heat it underneath. So that's all set up nicely. And Paul's going to fill this up with water. And then it comes back beautifully filled with water. Unfortunately, he did manage to get the outside wet, so he's going to pass me a paper towel. Thank you, Paul. There. Right, so this is full of cold water, and we're ready to have a go. I'm going to take again one of these little crystals. And let's carefully drop it in. Okay, so we've now got a crystal in there, and it will start to release dye. I think it's a little bit high, so I'm just going to pull it down just a tad more. I want to try and make sure that it's reasonably level. And what I don't want to do is anything to sort of happen. And I'm giving it a moment while I waffle, just so this dye starts to sort of dissolve here. So I've got a little bit of dye that we can actually see doing something. It works better in warm water, it dissolves better, but of course that then ruins this experiment. So I've got now a little bit of dye there, I can see. So let's start the experiment. I'm going to heat up this corner. So I'm going to heat this corner, and the water is going to start to get hot, it's going to rise, and as that happens, it should start to move the dye along. Don't know if you can see, but the dye is moving along here. And now it's starting to make its downward way down this side. Because we've set up a circulation. So this side's hot, it's rising, and it's picking up the dye there, and that dye is then being carried around. Let's do a little bit more heating. Now we can see the dye moving around. Back a little bit more. The only trouble is the dye starts to turn the whole thing pink very quickly, and then we can't really see what's going on. But we can see the dye moving down this arm, and hopefully you saw it move up the other arm. I could see it, whether you could. I'll have to see later in the video. So we've got here convection, the movement in here a liquid. Okay. We'll just get rid of that one out of the way for the time being. And we'll have a look at then convection again, but this time I want to have a look at it in a gas. Paul's going to move the camera down so you can see what's going on. What I have is a box, and at one end we're going to place a chimney, and the other end we'll put a chimney. I'm going to put a candle at this end underneath this chimney. And let's light the candle. So the candle's going to burn. Close the door. And the candle is right under this chimney. And if I put my hand here, I can feel the heat from the candle rise. Now, what's going on? Well, let's see convection working. I'm just going to burn a piece of string. Having blown it out, I can then hold it in the path of this chimney, and you might be able to see the smoke being sucked down this tube, moving along here, and I don't think you're going to probably see it coming out. I can just see little wisps of smoke coming out this side. The string continues to smoulder quite well because air is being sucked in this chimney. As it rises out of this one, and I can see some of the smoke coming out. And there, that's gone out. So we have here convection occurring in a gas. The gas is heated, this side rises up out here. As it rises up here, then more air is sucked in to fuel the flame. And we've got a cycle going on, except this bit outside, of course, is the rest of the world. So there we have convection. Right, let's go back and have a look at what we've done. So we've got convection. We've looked at a couple of experiments, really. 3 I know, but 2 are the same, really. We've got, first of all, we've got a beaker, and this is full of cold water. We supply heat at this particular point, and we see it sort of rising up in the center, and in theory it goes to the sides and then comes down. So what we've got is heat going in, if you like, a circle round like that. We showed that better in the next experiment. This is why it's better to do experiments than watch my drawings, because my drawings are particularly awful. We placed a crystal here, heated at this point, and the molecules here become less dense. And therefore the warm water here rises. And so we set up a flow in this direction. So we've got here this idea of convection. We can look at exactly the same process, but this time in air. And if we look at convection in air, then what we had was a box with two chimneys and a flame under one. The warm air rose, so therefore cold air was sucked in down this chimney and fed the flame with more oxygen, thus setting up this cycle. So we can see that we've got with convection basically a cycle going on, that we've got things happening. We can't see them always, and if I have a look at a picture of a room, and let's put in a radiator in the room. Radiator's rather a stupid name for a convection heater, which is what it is, but I don't make the rules. I didn't invent the name. I just live with it. Generally, if you've got a radiator, you put that under a window because that's the coldest air in the room. The radiator heats up, the warm air rises, and it will heat that cold window. The heat then will travel across the ceiling, showing the warmest part of the room is probably in the ceiling. So if you come in on a cold winter's day, try and remember to stand on the ceiling and it will keep you warmer. And then this colder air will sink, ready to be heated by the radiator again, setting up this convection current. So there's our convection current in a room going. Now, let's see what else we've got. We've got one other form of heat, and the other form of heat that we can look at is that of radiation. I want to try to show you radiation in a couple of ways. The first of these is I've got a small camera. This is an FLIR camera, and I'm going to try and use this. This attaches to my mobile phone, and with a bit of luck, I might be able to get this to work. So we'll try this and see if this one works. And what I'm going to look at is an item called a Leslie cube. Basically, a Leslie cube has different surfaces that are different colors. And we're going to use my infrared thermometer to have a look at this. And we're going to look at the heat that's radiated out and see what happens. And with a bit of luck, we might be able to take a thermal picture of this, and we might see something, although I don't guarantee it. Let's go and have a look at this. So Paul's just going to reheat the water for me in the kettle. Just quick tidy. Unfortunately, can't quite get enough staff in to get everything done. So we're going to place on here a Leslie cube. Here is the Leslie cube. It's a metal container, and it's got a mucky white surface here. Just give that a quick clean. That's probably going to help the experiment a little bit. We've got a white surface. We've got a bare metal surface here. It's just the metal. This side is a rough matte surface, and this side is a shiny black surface. And what I'm going to do is I'm just going to get out the thermal thermometer and just shine it on here, and we can see that's 25.6, that's 23.7, 25, 25. So they're all much of a muchness. Slight difference, and we'll worry about some of those differences in a minute. And in a moment I'll get Paul to set up the thermal camera for me. But first of all, Paul's going to pass me the kettle. What I'm going to do is I'm going to fill this with hot water. Have to be careful doing this. If you just put this in too tightly, air can't get out. So I'm going to just hold this a little bit and start filling this with hot water. What I want to do is fill this up as full as I can. From experience, it's a whole kettle full. And there we have this full. So we've got the different surfaces. So let's have a look at the surfaces in turn. And if I try this on here, I've got 88.7, 88.8. This is the shiny black surface. Let's turn it around. This is the matte black surface. 88. Yeah, 88 dead. So we had 87.5. That's 89 now. The metal surface, 73. And the white surface coming in here, 90.4. So 90.4. The black one, 89. The rough black one, 89.3. And this metal surface, now it says it's about 75, 76. So there is a difference here. And Paul set up the FLIR camera. Is it working? Right, so can you position the FLIR camera in front of this camera so we can see what's going on? Flip back a little bit. And this is the FLIR camera working. You can see how full I've actually got this. And we've got a measure of the temperature here anyway, measuring the temperature. I'll turn it round. And Paul can see the difference in temperature. This is now the shiny black surface. And there's our white surface. So the FLIR camera is giving an indication of what's going on. So it does work quite nicely. And if Paul's very clever, I'm just going to sit down and Paul's going to take an FLIR image of me. And he's quite entertaining trying to watch what Paul's having to do here by moving the camera and his arm to get two different cameras all set up working in the right place. But hopefully I can see a picture of me. There we are. I have to look the other way to see me, and I can see that I've got quite a white face here. I'm quite hot, whereas some of the background is much cooler. So the FLIR camera, quite good. It's great fun to take this one outside at night when it's really dark, and I stand out a mile because I can be seen beautifully. Okay, thank you, Paul. So there we've got the radiation. We saw that we had different surfaces. We had white and we had black. And these surfaces, when we look at them with the infrared thermometer, the white seemed to be giving out the most temperature. The most heat was coming out there. And the black surface was giving out less. And around this side, we couldn't see the metal surface. And that was by far the poorest. So that was the porous radiator. So it appears that white seems to be the best color for radiators. It's going to give out more heat than if you just took an ordinary radiator and didn't bother to paint it. If you have to paint it, then, well, even black seemed to work quite well. And if we looked at it with the FLIR camera, and that is just an infrared camera, we can see that we get quite good sort of images of all types of things. So we've looked at very simply here conduction, convection, and radiation. Three means of transferring heat. Conduction works simply with solids. Convection works with gases and liquids, as we saw. And radiation, well, the energy from the sun's got to get here somehow. And put your hand up to the sun, if you can spot it, and you can feel the heat from the sun. So there we are. We've looked at those. Next time we'll have a look at a little bit more with heat and move on and look at perhaps specific heat capacity. Until then, I'll see you next time. Thanks for watching. Bye-bye.